I welcome you all in our today's session, that is constraint propagation, that is interference in CSPs. CSP stands for constraint satisfaction problems. In regular state space search, an algorithm can do only one thing, that is search. In CSPs, there is a choice. An algorithm can search, choose a new variable assignment from several possibilities, or do a specific type of inference called constraint propagation, using the constraint to reduce the number of legal values for a variable, which in turn can reduce the legal values for another variable, and so on. Constraint propagation may be intertwined with search, or it may be done as a pre-processing step before search starts. Sometimes this processing can solve the whole problem, so no search is required at all. The key idea is local consistency. If we treat each variable as a node in a graph and each binary constraint as an arc, then the process of enforcing local consistency in each part of the graph causes inconsistent values to be eliminated throughout the graph. There are different types of local consistency, which we now cover in turn. What are those local consistency? First one is the node consistency. A single variable corresponding to a node in the CSP network is node consistent if all the values in the variable's domain satisfy the variable's unary constraints. For example, in the variant of the Australia map coloring problem, where South Australians dislike green, the variable SA starts with domain red, green, blue, and we can make it node consistent by eliminating green, leaving SA with the reduced domain red, blue. Here we eliminated green. We say that a network is node consistent if every variable in the network is node consistent. It is always possible to eliminate all the unary constraints in a CSP by running node consistency. It is also possible to transform all n-array constraints into binary ones. Because of this, it is common to define CSP solvers that work with only binary constraints. The next is the arc consistency. A variable in a CSP is arc consistent if every value in its domain satisfies the variable's binary constraints. More formally, xi is arc consistent with respect to another variable xj if for every value in the current domain di there is some value in the domain dj that satisfies the binary constraint on the arc xi and xj. A network is arc consistent if every variable is arc consistent with every other variable. For example, consider the constraint y is equal to x raised to 2 or x square, where the domain of both x and y is the set of digits. We can write this constraint explicitly as x comma y 0 0 1 1 2 4 3 9. To make x arc consistent with respect to y, we reduce x domain to 0, 1, 2, 3. If we also make y arc consistent with respect to x, then y's domain becomes 0, 1, 4, 9 and the whole CSP is arc consistent. On the other hand, arc consistency can do nothing for the Australia map coloring problem. Consider the following inequality constraint on SAWA. Red green, red blue, green red, green blue, blue red, blue green. No matter what value you choose for SA or for WA, there is a valid value for the other variable. So, applying arc consistency has no effect on the domains of either variable. The most popular algorithm for arc consistency is called AC3, which is shown in the next figure, figure number 1. To make every variable arc consistent, the AC3 algorithm maintains a queue of arcs to consider. Actually, the order of consideration is not important. So, the data structure is really a set, but tradition calls it a queue. Initially, the queue contains all arcs in the CSP. This is our figure number 1, which shows the arc consistency algorithm AC3. So after applying this AC3, either every arc is arc consistent or some variable has an empty domain, indicating that the CSP cannot be solved. The name AC3 was used by the algorithm's inventor, that is McWorth, because it's the third version developed in the paper. AC3 then pops off an arbitrary arc xi xj from the queue and makes xi arc consistent with respect to xj. If this leaves di unchanged, the algorithm just moves on to the next arc. But if this revises di, makes the domain smaller, then we add to the queue all arcs xk, xi, where xa is a neighbor of xi. We need to do that because of the change in di might enable further reductions in the domains of dk, even if we have previously considered xk. If di is revised down to nothing, then we know the whole CSP has no consistent solution and AC3 can immediately return failure. Otherwise, we keep checking, trying to remove values from the domains of variables until no more arcs are in the queue. At that point, we are left with a CSP that is equivalent to the original CSP. They both have the same solutions, but the arc consistent CSP will in most cases be faster to search because its variables have smaller domains. The complexity of AC3 can be analyzed as follows. Assume a CSP with n variables, each with domain size at most d and with C binary constraints, that is arcs. Each arc xk xi can be inserted in the queue only d times because xi has at most d values to delete. Checking consistency of an arc can be done in O of d raised to 2 times. So we can get O of c d raised to 3 total worst case times. Now it is possible to extend the notion of arc consistency to handle an array rather than just binary constraint. This is called the generalized arc consistency, or sometimes it is also known as the hyperarc consistency. The variable xi is generalized arc consistent with respect to an n-array constraint if for every value v in the domain of xi there exists a tuple of values that is a member of the constraint. It has all its values taken from the domains of the corresponding variables and has its xi competent equal to v. The next consistency is the path consistency. The arc consistency can go a long way toward reducing the domains of variables, sometimes finding a solution by reducing every domain to size 1, and sometimes finding that the CSP cannot be solved by reducing some domain to 0. But for other networks, arc consistency fails to make enough inferences. Now consider the map coloring problem on Australia, but with only 2 colors allowed, red and blue. Arc consistency can do nothing because every variable is already arc consistent. Each can be read with blue at the other end of the arc or vice versa. But clearly there is no solution to the problem because Western Australia, Northern Territory and South Australia all touch each other. We need at least 3 colors for them alone. So arc consistency tightens down the domains, it is unary constraint, using the arcs, which is binary constraint. To make progress on problems like map coloring, we need a stronger notion of consistency. Path consistency tightens the binary constraints by using implicit constraints that are inferred by looking at triples of variables. A 2-variable set xi xj is path consistent with respect to a third variable xm if for every assignment this xi is equal to a and xj is equal to b, consistent with the constraints on xi xj. There is an assignment to xm that satisfies the constraints on xi xm and xm xj. This is called path consistency because one can think of it as looking at a path from xi to xj with xm in the middle. Now let's see how path consistency fares in coloring the Australia map with 2 colors. We will make the set WA-SA path consistent with respect to NT. We start by enumerating the consistent assignments to the set. In this case, there are only 2. WA is equal to red and SA is equal to blue, and WA is equal to blue, SA is equal to red. We can see that with both of these assignments, NT can be neither red or blue because it could conflict with either WA or SA. Because there is no valid choice for NT, we eliminate both assignments and we end up with no valid assignments for WA-SA. Therefore, we know that there can be no solution to this problem. The PC2 algorithm, which is invented by Mackworth in 1977, achieves path consistency in much the same way that AC3 achieves arc consistency. The next consistency is the K consistency. Stronger forms of propagation can be defined with the notion of K-consistency. A CSP is K-consistent if for any set of K-1 variables and for any consistent assignment to those variables, a consistent value can always be assigned to any kth variable. One consistency says that given the empty set, we can make any set of one variable consistent. This is what we called as the node consistency. Two consistency is the same as arc consistency. For binary constraint networks, three consistency is the same as path consistency. A CSP is strongly K-consistent if it is K-consistent and is also K-1 consistent, K-2 consistent, and so on, all the way down to 1 consistent. Now suppose we have a CSP with n nodes and make it strongly n consistent, that is strongly K consistent for K is equal to n. We can then solve the problem as follows. First, we choose a consistent value for x1. We are then guaranteed to be able to choose a value for x2 because the graph is 2 consistent, for x3 because it is 3 consistent, and so on. So for each variable xi, we need only search through the d values in the domain to find a value consistent with x1 up to xi minus 1. We are guaranteed to find a solution in time O of n raised to 2 into d. Any algorithm for establishing n consistency must take time exponential in n in the worst case. Worse, in n consistency also requires space that is exponential in n. The memory issue is even more severe than the time. In practice, determining the appropriate level of consistency checking is mostly an empirical science. It can be said practitioners commonly compute 2 consistency and less commonly 3 consistency. So what are the global constraints? Remember that the global constraint is one involving an arbitrary number of variables but not necessarily the all variables. Global constraints occur frequently in real problems and can be handled by special purpose algorithms that are more efficient than the general purpose methods described so far. For example, the all-def constraint says that all the variables involved must have distinct values, as in the cryptarithmetic problem and Sudoku puzzle below. One simple form of inconsistency detection for all-def constraints works as follows. If m variables are involved in the constraint and if they have n possible distinct values altogether and m is greater than n, then the constraint cannot be satisfied. This leads to the following simple algorithm. First, remove any variable in the constraint that has a single tone domain and delete the variable's value from the domains of the remaining variables. Repeat as long as there are single tone variables. If at any point an empty domain is produced or there are more variables than domain values left, then an inconsistency has been detected. This method can detect the inconsistency in the assignment. WA is equal to red, NSW is equal to rate. For figure 2, we notice that the variables SA, NT and Q are efficiently connected by an all-diff constraint because each pair must have two different colors. After applying AC3 with the partial assignment, the domain of each variable is reduced to green and blue. So this figure here shows the principal states and territories of Australia. Coloring this map can be viewed as a constraint satisfaction problem, this CSP. The goal is to assign color to each region so that no neighboring regions have the same color. The map coloring problem represented as a constraint graph here. That is, we have three variables and only two colors, so the all-diff constraint is violated. There is a simple consistency procedure for the higher order constraint is sometimes more effective than applying arc consistency to an equivalent set of binary constraints. There are more complex inference algorithms for all-diff that propagate more constraints but are more computationally expensive to run. Another important higher order constraint is the resource constraint. Sometimes it is also called at most constraint. For example, in a scheduling problem, let P1, P2 up to P4 denote the number of personnel assigned to each of 4 tasks. The constraint that no more than 10 personnel are assigned in total is written as at most 10 P1, P2, P3, P4. We can detect an inconsistency simply by checking the sum of the minimum values of the current domains. For example, if each variable has the domain 3, 4, 5, 6, the at most constraint cannot be satisfied. We can also enforce consistency by deleting the maximum value of any domain if it is not consistent with the minimum values of another domain. Thus, if each variable in our example has the domain 2, 3, 4, 5 and 6, the values 5 and 6 can be deleted from each domain. For large resource limited problems with integer values such as logistical problems involving moving thousands of people in hundreds of vehicles, it is usually not possible to represent the domain of each variable as a large set of integers and gradually reduce that set by consistency checking methods. Instead, domains are represented by upper and lower bounds and are managed by bounds propagation. For example, in an airline scheduling problem, let's suppose there are two flights F1 and F2 for which the planes have capacities 165 and 385 respectively. The initial domains for the number of passengers on each flight are then D1 is equal to 0, 165 and D2 is equal to 0, 385. Now suppose we have the additional constraint that the two flights together must carry 420 people. It is F1 plus F2 is equal to 420. Propagating bounds constraints, we reduce the domain to D1 is equal to 35, 165 and D2 is equal to 255, 385. We say that the CSP is bounds consistent if for every variable x and for both the lower bound and upper bound values of x, there exists some value of y that satisfies the constraint between x and y for every variable y. This kind of bounds propagation is widely used in practical constraint problems. Now we will consider the Sudoku example here. The popular Sudoku puzzle has introduced millions of people to constraint satisfaction problems, although they may not recognize it. A Sudoku board consists of 81 squares, some of which are initially filled with digits from 1 to 9. The puzzle is to fill in all the remaining squares such that no digit appears twice in any row or column or 3 by 3 box, which is as shown in the figure 3. A row, column or box is called a unit. Here the figure shows the Sudoku puzzle and the figure B shows its solution. The Sudoku puzzles that are printed in newspapers and puzzle books have the property that there is exactly one solution. Although some can be tricky to solve by hand, taking tens of minutes, even the hardest Sudoku problems yield to a Csp solver in less than 0.1 second. A Sudoku puzzle can be considered a Csp with 81 variables, one for each square. We use the variable names A1 through A9 for the top row, that is left to right, down to I1 through I9 for the bottom row. The empty squares have the domain 1, 2, 3, 4, 5, 6, 7, 8, 9. And the pre-filled squares have a domain consisting of a single value. In addition, there are 27 different all-diff constraints, one for each row, column and box of 9 squares. All-diff A1, A2, A3, A4, A5, A6 up to A9, all-diff B1 up to B9, all-diff A1, B1, C1, D1, E1, F1, G1, H1, I1, all-diff A2, B2, C2 up to I2, all-diff A1, A2, A3, B1, B2, B3, C1, C2, C3, all-diff A4, A5, A6, B4, B5, B6, C4, C5, C6 and so on. So let us see how far our consistency can take us. Assume that the all-diff constraints have been expanded into binary constraint such as A1 is equal to A2, so that we can apply the AC3 algorithm directly. Now consider variable E6 from figure 6, that empty square between the 2 and 8 in the middle box. From the constraints in the box, we can remove not only 2 and 8 but also 1 and 7 from E6 domain. From the constraints in its column, we can eliminate 5, 6, 2, 8, 9 and 3. That leaves E6 with the domain of 4. In other words, we know the answer for E6. Now consider the variable I6, the square in the bottom middle box surrounded by 1, 3 and 3. Applying R consistency in its column, we eliminate 5, 6, 2, 4, since we know A6 must be 4, 8, 9 and 3. We eliminate 1 by R consistency with E5 and we are left with only the value 7 in the domain of I6. Now there are 8 known values in column 6. So R consistency can infer that A6 must be 1. The inference continues along these lines and eventually AC3 can solve the entire puzzle. So all the variables have their domains reduced to a single value as shown in the figure 3b. Of course, Sudoku would soon lose its appeal if every puzzle could be solved by a mathematical application of AC3, and indeed AC3 works only for the easiest Sudoku puzzles. The slightly harder ones can be solved by PC2, but at the greater computational cost. There are almost 2,55,960 different path constraints to consider in a Sudoku puzzle. To solve the hardest puzzles and to make efficient progress, we will have to be more clever. That strategy works as follows. In any unit, that is row, column or box, find 3 squares that each have a domain that contains the same 3 numbers or a subset of those numbers. For example, the 3 domains might be 18, 38 and 138. From that, we could know which square contains 1, 3 or 8. But we do know that the 3 numbers can be distributed among the 3 squares. So therefore, we can remove 1, 3 and 8 from the domains of every other square in the unit. It is interesting to note how far we can go without saying much that is specific to Sudoku. We do of course have to say that there are 81 variables, that their domains are the digits 1 to 9 and that there are 27 all-diff constraints. But beyond that, all the strategies, arc consistency, path consistency, etc. apply generally to all CSPs, not just to Sudoku problems. So even neck triples is really a strategy for the enforcing consistency of all diff constraints and has nothing to do with Sudoku per se. This is the power of the constraint satisfaction problem formalism. For each new problem area, we only need to define the problem in terms of constraints. Then the general constraint solving mechanism can take over. So, in this section, we have seen the inference in CSPs with the constraint propagation. Okay, so here we have seen the different consistencies like arc consistency, path consistency, K consistency and so on. Okay, I hope this session will be helpful for your further studies. Thank you.